Hello, everyone. My name is Christopher Wheatley,
And I'm Matthew Bell.
and today we wanted to talk to you all about the practical concepts and applications of nuclear magnetic resonance spectroscopy, also known as NMR, for our 585 presentation.
All right, so let's walk through our learning objectives, the things we hope you guys take away today. Number one, we want you to be able to identify appropriate applications for NMR. Basically, why we want to learn this and where we can use it. Second learning objective is we want you to be able to understand the chemical and physical interactions that make NMR possible. Basically, why this is possible and be able to really understand and maybe even explain to somebody else. Number three, we want you to be able to understand the physical mechanism and construction of NMR machines, how they're built, this kind of basic idea of how we make an NMR machine. And then number four, be able to interpret NMR data plots and readouts for elemental information. We want to be able to give you plots and data from an NMR and you be able to tell us what it is. And so we'll just walk through a short history of kind of where NMR started. So in December of 1945 and January 1946, this kind of era is where these two independent groups were working on this kind of idea of NMR on a very physical and basic level. And so there were two physicists, basically. Felix Bloch, he was Swiss, and he was working at Stanford. And then Edward Purcell, he was an American physicist working at Harvard. And basically, these guys working independently were both able to figure out this phenomenon of NMR in solids and liquids, and that they were able to observe it. And so once everybody figured out how important this was, they were able to award them the Nobel Prize in Physics in 1952. And this kind of technology eventually leads with more and future research from future scientists leads to MRIs, which is a very important part of current medical dealings.
So, giving a little bit of the history, now we're going to go into NMR applications, what kind of use that it has to us as material scientists, and also to the world at large. So like Matt was saying, one of the most common uses now is for MRI, or magnetic resonance imaging, which has become very important in medicine. And we'll kind of see this pattern of NMR has become very important in organic and biological materials. And because of that, we thought that this was a particularly interesting characterization technique to look at. Because in the past, many of the characterization methods we've examined are designed for crystalline materials. For example, X-ray diffraction, it relies on either a monocrystal or a polycrystalline material for that pattern that we will see of the different planes and orientations. And so if you have an amorphous material like a polymer or a biological material, that is not going to be as effective for these crystalline patterns. But with NMR, its greatest strength is in these hydrocarbon-based materials, these organic materials. And so we'll see this gives us a way to characterize kind of these materials that we weren't able to do so before. Again, with these practical applications, it's become very popular in organic chemistry, and mostly due to the fact that NMR is very sensitive to hydrocarbons. We'll get to that in a little bit, but as materials engineers, we mostly see it being used in polymer science. So if you're to have a monomer, you want to find out what functional groups are part of this monomer that you're not, and you want to identify this monomer, you can use NMR to figure out those different functional groups are. And actually in the healthcare field, in addition to being used for MRI, it's also required that if you find a new organic compound or you find a new drug, for it to actually be identified and classified, you need to have an NMR scan done and submitted for it to be officially recognized. So another way that NMR is useful. It is popular in organic chemistry to that sensitivity to the hydrocarbons. And there's actually two main types, which is the hydrogen 1 based and carbon 12 or carbon 13 based. And so the hydrogen 1 is based off the hydrogen 1 isotope, where there is one single proton. And it is based off this isotope because it's unbalanced. You have an uneven charge. And this makes it one of the most common bases for NMR. It's also called proton NMR because that hydrogen 1 isotope is essentially a proton by itself. And because in some cases, you actually will have no hydrogen in a material, you can also use carbon-based or carbon-13. So carbon-12, that's the most common isotope of carbon. And it has no spin. It's a perfectly balanced atom. And so we have to use carbon-13 because it has an actual magnetic polarity to it. And we'll get into that. Matt will talk about that later. And so that is used instead, even though it is in fact less common, and so it's less sensitive to it. But this is a way that we can find and characterize purely carbon materials. For instance, you'll see on the bottom right, the Buckminster fullerene, or the buckyball, which is 60 carbon atoms in a spherical shape. This was actually characterized by this carbon-13 method because it is made up exclusively of carbon-to-carbon bonds. So a little pop quiz to just gauge your mind and get your mind going. So how much carbon-13 do you think is found naturally in a carbon group? So, most of it is going to be carbon-12, but how common do you think carbon-13 is found in a random sample? So just take a second, pause the video, think really hard. And once you've done that, the correct answer is 0.1%, so not a lot. But it really is a testament to the modern advances of NMR machines that they're still able to recognize these very minute amounts of carbon-13 enough to characterize these materials effectively. So it's still incredibly powerful.
All right, so next we're going to go through basically a kind of, hopefully, if it's a review of the quantum mechanical model. If not, it's going to be a very, very, very fast crash course of what we're going to be using for NMR. This is a lot of times learned in modern physics class. Sometimes people haven't taken that yet, or weren't required to take that. But basically, the book we mainly use for this is up in the top right there. It's NMR Spectroscopy. It gives a good review of the required modern physics knowledge. Okay, so one of the main ideas, I know in my physics class we spent a good amount of time deriving this idea, but the idea you come away with is that the energy of an atom is restricted to discrete energy levels. It's not continuous or like a spectrum of energy that it could possibly be. It is designated energy levels, and it's not by magic. It's by proven things that we won't have enough time to go into today. And so we call these energy states, and they're one of the most important ideas and the basic idea behind NMR, which we will get to. And so to basically help quantize these energy levels, a lot of times it's with electrons, but in our case, it's going to be with the nucleus too. We get these 4 quantum numbers, and I'm sure you've probably heard of these. It's N, which is the principal quantum number, L, which is the angular momentum. The book we're going to use is actually, it uses P instead of L, but same thing, angular momentum. M sub I is the magnetic quantum number, and M sub S is the spin quantum number. And those last two are what we're going to focus on. There are a lot of why NMR behaves the way it does. And so then, a couple quick things back on the previous slide. M sub I is dependent on angular momentum, I or L, or in the book's case, P. And so that's something to keep in mind when we're deriving equations. And then MS can only have values of +1/2 or -1/2. Those are the rules that modern physics proves, and we're just going to use them here. Okay, so now we're just going to do a quick quiz question here. Just kind of looking back at what I've talked about so far. So how do we best describe the energy of a nucleus? I've harped on this a lot, but I want to make sure we understand before moving on. How do we best describe this? So take a minute, pause the video, write this down, and we'll come back and discuss the answer. Okay, so we're back. And so the answer is not continuous. I know I'm harping on this, but this is a very, very important idea when talking about NMR. Energy is not continuous. It is discrete. It can only be on certain levels. It can't be in between the levels. This type of idea is very important. Okay, so we'll dive into basically using this a quantum mechanical model for an isolated proton. Okay, now keep in mind throughout these slides, it's for an isolated proton. It's not for a full nucleus. Okay, so if you take one proton away, it's kind of like thinking of a hydrogen atom without an electron. You get one of the main ideas you get is your magnetic moment, which is mu, equals gamma, which is called the magno-gyric ratio. It's just a constant that is specific to each nucleus. And that's times your angular momentum P, which was L in the previous. We're going to use P now. And so this is kind of one of the basic things we get from nuclear physics. And we're not going to go into that very far, but this is the main idea you get from that. And as well, from previous modern physics knowledge, we know that angular momentum P is equal to h bar times m sub I. M sub I is your magnetic quantum number, and h bar is your reduced Planck's constant, which is just Planck's constant is up on the top right there, and h bar means it's just Planck's constant divided by 2 pi. Now, going through all that, after we combine these, we get to mu z equals m sub I times gamma times h bar, which is your magnetic moment is equal to your magnetic, you get it in terms of your magnetic quantum number and then 2 constants, which is a very easy equation. And now you can sub in what your known value of m sub I is. And so for an isolated proton, due to its behavior, we know it's either plus 1/2 or minus 1/2, just depending on which one we're talking about. And so it can have 2 discrete energy levels. And so that's how we get that bottom equation there. And so this, you can kind of picture this as a magnetic dipole because it has the magnetic moment can have 2 possible values, and it's equal and opposite of each other. So then going along with this, so on the right there, that's kind of the magnetic dipole I was talking about. That's kind of a visual representation of it. And so those black arrows are what we were talking about. It's 2 magnetic moments equal and opposite in direction, or not direction, but equal opposite in sign. And so that's without a magnetic field applied, which is B sub 0. They're called degenerate, so they have the same energy. Now, once we apply a magnetic field to these already magnetic moments, we create energy. And so these can be represented by the potential energy of a magnetic dipole equation, which is E equals mu z, which is your magnetic moment, times the applied magnetic field. Now, using the previous equation that we came up with in the last slide, and combine it with that E equation, we can now get your potential energy in terms of your magnetic quantum number, 2 constants, gamma, which is specific to the nucleus, h bar, which is just a universal constant, and then B0, which is your applied magnetic field. Now, the visual representation on the left there is showing B sub 0 basically on the bottom axis there. And so you can think of as this applied magnetic field is increased, your delta E is going to increase. Delta E is the difference between the 2 energy levels we were talking about due to that plus 1/2 and minus 1/2 of m sub I. Now, we can get an equation for delta E just by taking the difference between these 2 energies. And that's that equation, delta E equals gamma times h bar times B sub 0. Now, it's called the Bohr frequency condition. It's another modern physics thing that we won't get into too much, but one of the derivations you can get from that is delta E equals h, which is Planck's constant again, times B, which is frequency. Now, the main idea here is you think of these energies in terms of waves, so they'll have a frequency here. Now, combining those 2 equations, we get this equation in the middle here, H times your frequency equals gamma times H bar times your magnetic field applied. Now, this is the most important part here because this is how we get a frequency. And that's what we're measuring here. That's this resonance is what we've been trying to get to the whole time. That's what's resonating is this, we're trying to measure this frequency. Now, important thing to remember here is that this was only for a single proton, so it gets a little more complicated with a larger nucleus, and we won't be able to get into that, but this is the main idea associated with why nuclear magnetic resonance works. It's because you have these discrete energy levels, two possible energy levels, and this delta E. From delta E, you can get this frequency, and you can measure the frequency. Now, there's this thing called chemical shift, basically. And so what happens is when you get into bigger molecules with larger nuclei and electrons surrounding the nuclei, they each have their own magnetic field associated with them. And that can affect the larger magnetic field applied, which also affects your magnitude, which affects B sub zero. And so once affecting that, you get this chemical shift associated, which now this value of frequency you're looking for, it's now like a spectrum sometimes or a shift. And so that's why this becomes pretty important in terms of chemistry and biology, is this chemical shift effect. Okay, so with all that in mind, we'll do a quick question here. So given what I've just said to you, that big rants about all that modern physics, how do you think NMR works? I kind of gave it to you in the last question, but I just want us to be able to brainstorm and give some ideas of how we think this is going to work. So pause the video and do that real fast. Okay, so now we're back. And so kind of we'll go through now how NMR works just in general. I think we have a good idea, but let's just get it on out there. And again, this is just basically, again, going through this NMR book. I didn't say this before, but you can get it through UKY Library. It's just an easy download of it. And it's very helpful when understanding this NMR spectroscopy. Okay, so what happens is you have an NMR tube and you place the sample in the tube, okay? Now, this sample is going to have a magnetic moment associated with the nucleus. That's what we kind of went through with the isolated proton, but this nucleus is going to have a associated magnetic moment. And then we apply a magnetic field to this sample. And so when we do that, it's creating these energy levels, this nuclear energy level diagram you see going on the right there. And so now you have these different discrete energy level states with a delta E associated with them. And so going from there, we can get these using a radio frequency transmitter. We can now stimulate these transitions, measure the spectral line that comes out after we've measured these stimulated these transitions. And now we can, using that resonance signal and this data output that we'll show you later, we can now determine what elements we have.
Okay, so we talked a lot about the theory, but going more on the application side of things, these are how we take this magnetic resonance theory and put it into action. So NMR machines, as you saw on the previous slide, I talked about a test tube, and you can see the NMR test tube here at the top right. And then for that is inserted into the NMR machine, which you can see on the bottom right. And so the sample is dissolved and it's put into this test tube and put into the center of this machine. And then you use electromagnetics made out of superconductors. And so you can see here that there are kind of two inner shells. One is liquid nitrogen. That's the larger kind of space. And then inside that is liquid helium. And that's just to get these temperatures that are so cold that we start to see superconducting for the electromagnet. And so kind of use the nitrogen in a larger space because it's cheaper and also it's not as cold. And then for the really cold inner core, you use the liquid helium. to kind of reduce cost and ease of testing. And so the superconducted electromagnetics take it down to and actually start superconduction so we can have these really powerful magnetic fields. So the tube is kind of spinning throughout, and you have radio frequencies or RF waves that are affecting the sample when you have this additional magnetic field the machine is making. And so kind of these interactions between the tube itself and the electromagnetic, these are taken back and transmitted into usable visual data that we can actually use to figure out what this sample is and what kind of compounds it has inside of it. So you can see kind of here at the bottom right, the tube spinning, interacting with the electromagnets, and this RF signal is being sent down to a console, which is this really big machine right here. That console is what turns this radio frequency information into the kind of plots that we'll see to figure out these different compounds, which you'll see on a standard computer. Okay, so we kind of talked about the theory behind it, and we talked about how these machines work, but if you're given this visual data, how can you read it and know what's going on? What kind of material are you looking at? So looking at this, earlier you may have heard Matthew talk about chemical shifts, where different functional groups will have their own magnetic field special to that group. And because of this, you'll actually see a shift of them along the axis of their energies, of their magnetic field. And so we can actually use this to determine, based off of the reading, where it is on the line of what kind of functional groups we have in this polymer. And so you can see kind of your methyls, your ketones, your ethers, and several other different organic materials are included on this list. And then for the actual polymers themselves, here you have a group of ethylene, polyethylene, where in this case, the lines are what you would actually see during an NMR reading. And they're based off of the N+1 rule. So like you may have remembered, hydrogen 1 isotope is the most popular reading for NMR. And so we don't really care about the carbons in this scenario, but we care about what hydrogens that they're connected to. So this N+1 rule takes effect in, like if we were to look at A, we would say, okay, we don't care about the material, this part itself, we care about what's connected to it. So we would go to its only connection, which is here. And since it's hydrogen based, we say, okay, there are 2 hydrogens. So the 2 is equal to N, that's our N. It's an N+1 rule. So when we see the A on the visual graph, it would be 2 + 1 is 3. So we see the 3 lines here. In the same way over here, we don't care about this, but we see that it's also connected to these 2 hydrogens, 2 + 1. And so we see that 3 lines again. Now in the middle, you can see it's connected to 2 hydrogens over here and 3 hydrogens on the right. And so 2 + 3 is 5, 5 + 1 is 6. So that's why we see 6 lines here in the center for this particular molecule. And because each of these molecules is a little bit different, that's why they're all shifted as they are. And so looking at this, you can tell based off the shift and how many lines that there are, what kind of hydrocarbons we have. So I know that was a really basic example, but here's a somewhat basic example. It's again hydrogen based. So remember, you care about the hydrogens and what they're connected to. Can you give a guess of what this would look like with the chemical shifts of these different groups on the graph, and also how many carbons are attached to each? So using that N+1 rule and using the chemical shift table on the right, just give you a second to pause the video and take a look at what this would look like on an NMR graph. And welcome back. So looking at it, it would be kind of broken up again into the A, B, and C sections. So both of these groups are the same from their connection to what functional group they are. So you can see that they're actually included here together. So there's 1 hydrogen, N+1, 2 lines. And then B here on the center, it's actually connected to 1, 2, 3, 4, 5, 6. 6 plus 1 is 7, so you have 7 lines here. And then finally for this last hydrogen group here, it is kind of all by itself, that there are no hydrogens that it's connected to. So 0 plus 1 is 1 for the line. And you can see that this formational group right here isn't counted or recognized at all, because like we were saying, the NMR in this stage only cares about hydrogens. And so this is more or less invisible to it. But excellent work. So I hope that you all enjoyed learning a little bit about NMR, not just the theory, but also what we use to measure and characterize these different materials for, and also how to read a graph. So if you ever see one out in the wild, but thank you all very much.
Thanks, guys. Good luck with files and have a good break.